friends, here we are with the next lecture on convective heat transfer. Strictly speaking, the things that we have been discussing in the last few lectures and maybe even most part of today's lecture pertain to fluid mechanics, the understanding of the flow of fluids, although we are looking at the derivation of all the equations in a more generic fashion so that the study can be actually extended to the study of heat transfer, mass transfer as well as fluid mechanics together. So that we will be seeing in today's class or today's lecture. So in the previous class we actually understood the formalism of the Reynolds transport theorem, and using the Reynolds transport theorem we derived the basic differential equation for conservation of mass, momentum and energy, and we wrote those equations for a three-dimensional steady state system with incompressible flow for a fluid with constant properties. Okay, so this is the thing that we stopped in the previous class with. In today's class we will pick up from there and look at the behavior of those equations, look at the form of those equations for conservation of mass, momentum, energy and species, and look at the analogies or similarities between these equations and try to apply these equations to a situation of what we call an external flow, that is the flow outside the body of a solid. Okay. And we will understand a few concepts pertaining to that. We talked about boundary layer in the last class, so we will understand how these equations get simplified for boundary layers and how we get the solutions of these equations through an order of magnitude analysis, the form of the solution, and then we will resort to directly borrowing the mathematical results to get the final form of the equation, final form of the solutions. Okay. And from that we will understand how external flows normally behave. So that is basically what we have set out for today's class. So let's move on to the whiteboard. So in the last class we looked at the form of the various equations as let me write it now for a 2D incompressible steady state constant property flow. Okay, so the equation for conservation of mass becomes del u by del x plus del v by del y equal to 0. Okay. The x momentum equation looks like u del u by del x plus v del u by del y equals minus 1 by rho del p by del x plus nu times del squared u by del x squared plus del squared u by del y squared plus gx. So this is the conservation equation for momentum in x direction. Similarly for y momentum, the equation looks very similar. U del v by del x plus v del v by del y equals minus 1 by rho del p by del y plus nu times del squared v by del x squared plus del squared v by del y squared plus gy. Now in this we know that u and v are the momentum, the velocity components in the x and y directions respectively, and p is the pressure, rho is the density. The quantities that we may not be quite familiar with are the nu. We have actually talked about it some time before, but I'll write that again, and the quantity is called gx and gy. Nu is actually called the kinematic viscosity, which is actually equal to the coefficient of viscosity mu divided by rho. Okay, the coefficient of viscosity mu is the one that we normally know about from your school physics. That is, if I write the shear stress on any surface is proportional to del u by del y, which is the velocity gradient. The constant of proportionality is mu, so it's written as equal to minus mu del u by del y. This equation is quite similar in form to your Fourier conduction law, which basically says q dot double prime is equal to minus k del t by del y. Okay, so this is the analogous form. So just like your heat flux is proportional to the temperature gradient and the constant of proportionality is the thermal conductivity, which is a property of the medium, when a fluid flows past a surface, the shear force that it exerts, that is the force that if I have a surface like this and a fluid is flowing like this here, it exerts a drag on this surface, which is basically a shearing force on the surface, and that force is going to be proportional to the velocity gradient in that direction. Okay, the velocity gradient at the surface multiplied by a property mu, which is a property of the fluid. So if the fluid is more highly viscous, then for the same velocity gradient you will have a larger shear stress, and if the fluid is less viscous, that is the smaller value of mu, then it will have a smaller shear stress. So these two are quite analogous quantities, and this shear stress can be looked upon as the flux of momentum. That is, the fluid that is flowing is transferring its momentum to the solid surface by shearing the surface, by exerting a shear force on it, and therefore it can be looked upon as a flux of momentum. That is, the shear stress is the force per unit area, which is the momentum, the force per unit area, the shear force per unit area, which is the momentum flux. Okay, just like the heat flow per unit area, you get the momentum flow per unit area as a shear stress. Okay, so this nu is nothing but the kinematic viscosity, which is used here, and gx and gy are basically the body forces. Body forces are those forces which are exerted on every point inside the body. So if I have a fluid in gravitational field, the gravitational field has, let us say the vertical direction is y, so you have gy, which is present. So in gravitational field where the x, y, z are such that the y-axis is aligned with the negative or the direction opposite to the gravity, that is, the gravity is in the negative y direction, then this gx will normally be 0 in that case, and gy would be minus g. Okay, so the gy actually is shown in this direction, and actually g is in the downward direction, that's why it's a minus g. Okay, so that is normally you get. So this is basically when the whole substance is present in the gravitational field. Okay. When it is present in an electric field or magnetic field, for example, an electrostatic precipitator where particles are attracted by electrostatic field starting from the corona discharge of a wire, and eventually they migrate towards grounded plates, there the forces that are there would be in terms of the electric field forces rather than the gravitational field forces. So such field forces which are exerted over all parts of a given body are called the body forces. So the gx and gy are body forces. When the gravitational forces are negligible as compared to the other forces in the fluid, normally these terms are dropped, otherwise they are kept in the equation. Okay, so this is your 2D incompressible steady state constant property flow mass and momentum equations. Okay, so in the same fashion we can write the energy equation, okay, which will have u del t by del x plus v del t by del y is equal to k over rho c. This we would write it as alpha in place of k by rho c multiplied by del squared t by del x squared plus del squared T by del y squared. Okay, and if there is a heat source, then there is a Q dot triple prime generation. Otherwise, that is not there. So this is your energy equation. In the same fashion, if I have a multi-component system, say for example, suppose I have a plate, okay, which is actually a slab of salt, okay, and you have water that is flowing on top of it. Far away from the plate or far away from the slab, the water has zero concentration of salt, and at the surface the salt concentration would be determined by the solubility of the salt in water. So you would have a certain Cs and there is a certain C infinity. Okay, so there is a variation in concentration of salt when there is a flow here. So this would start from a value which is non-zero and eventually go to zero. Okay, so it can go to zero, it can go to, suppose this itself is a salt solution with a lower concentration of salt, then the C infinity will have a non-zero value. So you can actually have the concentration going like this here. So now if I look at the conservation equation for the transport of the salt from the slab to the fluid, it would obey a similar equation. So you are at the surface, you will have what is called the Fick's law of diffusion, which says the J dot double prime of salt in this particular case, which is the mass flux of the salt, would be proportional to del C by del Y at this location. So it would be equal to minus D times del C by del Y, where D is the diffusivity of the salt in this medium. Okay, so it's a property of actually the solute and the solvent put together. It's a solute solvent pair thing. So this is the diffusivity of salt in this medium multiplied by. So this also has a very similar form to the previous two expressions that we saw. The shear stress, which is proportional to the velocity gradient, the heat flux, which is proportional to the temperature gradient, and here you have the mass flux, which is proportional to the concentration gradient. And applying this in deriving the equation of transport, we will get the species equation, which is the conservation of mass of individual species that you would get, or it is written in terms of the concentration, which is nothing but the number of moles of a particular species per cubic meter of the solution. So you will get U del C by del X plus V del C by del Y is equal to D by rho, okay, of del squared T by del squared C by del X squared plus del squared C by del Y squared Okay, so actually the D by rho does not appear here, it actually comes out in the form of D, so there should be a rho in this one. Okay, so basically this is the form in which this equation appears. So now you see that this equation, and you can have plus the rate of generation, so N dot triple prime generation. So if there is a chemical reaction in which a species is produced, then that term would be present just like heat generation term here. So this would be another equation, and this equation is also very similar to this equation, or for that matter these two equations. All of these equations have very similar form, except there are additional terms because of pressure force and body force in the momentum equation, which are not present in the other two, but instead you have the generation terms that are present. Okay, so but the form of the equation has the convection in the x direction, convection in the y direction, or advection in the x direction, advection in the y direction, conduction or diffusion in the x direction, diffusion in the y direction. Similarly, advection x direction, advection y direction, diffusion in x direction, diffusion in y direction. In the same way, in this case, advection in x direction of momentum, advection in y direction of momentum, and the diffusion in x direction and diffusion in y direction because of viscosity. Okay, so you can basically look upon all of these equations as what you call as advection diffusion equations or convective transport equations. Okay, so this is an interesting fact that all of these equations have very similar forms. When we apply it to a particular case, we can even find that these equations as well as boundary conditions take similar forms, in which case the solutions of these equations also are very similar to each other, subject to a few parameters. Let us try to apply this set of equations to a flat plate boundary layer. A flat plate boundary layer is one of the simplest external flow conditions. So what we have is, here we have a flat plate, okay, which starts from here. Let us say this is a plate. Okay, there is nothing below the plate. We don't consider anything below the plate. So there is a flow that is coming here with a velocity u infinity, and maybe with a temperature of T infinity and concentration of C infinity, where the surface has u is equal to 0 and v is equal to 0 because of no slip, the stationary plate. Therefore, the two velocity components there are 0, and T is equal to, let us say, Ts, and C is equal to, let us say, Cs, the temperature of the surface and concentration at the surface. Then actually, as we saw in the earlier class, there is at any location, if I look at the variation of velocity, the u would go something like this, where u is 0 at the surface because of the no slip condition, and far away from the plate it is u infinity. So between the far field and the plate there is a minor variation, and this thickness of the fluid layer over which the velocity goes from 0 to u infinity, or let us say this goes to u infinity at, let us say, y tending to infinity, if this is the y direction and this is the x direction, starting from x is equal to 0 at the leading edge of the plate, this is the x direction. Then you will find that this layer, where let us say the velocity reaches 99% of the free stream velocity, that is u reaches 0.99 times u infinity, that if I call it as the edge of the layer affected by the presence of the plate, that edge actually is right at the plate here, and it grows gradually. So you will get a variation like this, where if I call this as thickness delta, which is a function of x, then you have what we call as boundary layer. Okay, so this region which is under this dotted line, which is an imaginary dotted line, of course, that we have drawn, the region within this dotted line is a region that is affected by the presence of the plate, and the region beyond that dotted line is a region which is unaffected by the presence of the plate and therefore would remain at the free stream conditions. Then if I want to understand the effect of the presence of the plate or the effect of the free stream on the plate in terms of momentum transfer, heat transfer, or mass transfer, then all the equations that I need to solve, the equations that I wrote down, need to be solved in this region, which is the boundary layer. Okay, so the region of my interest for understanding external flows is the region which is very close to the boundary layer. Normally the thickness of the boundary layer, the delta of x, is of the order of a few millimeters in the case of most of the applications. In large applications, like for example the flow over the wings of an airplane, whose span itself, the width itself, may be of the order of anywhere between 5 to 10 meters depending on the size of the aircraft, then the boundary layer thicknesses can grow to a few centimeters. Okay, but bulk of the applications that we normally look at, this momentum, the boundary layer is usually of the order of a few millimeters in thickness. Okay, so now much of the equations that we need to solve will need to be solved in this small thickness in the y direction. So the distances in the x direction, which I call as some characteristic length LC in the x direction, this would be much larger than the corresponding delta at any location. Okay, so the delta is much less than the corresponding x value. So this is a function of x. So delta at any given x is much less than the x value. This is what we call as the boundary layer approximation. Okay, so the boundary layer approximation simply states that the thickness of the boundary layer is much smaller than the characteristic dimensions of your object. That is, delta at any given x is much smaller than the x itself. Okay, so that is your boundary layer approximation. This is going to have very strong influence in simplifying the various equations that we have got already. Okay. Okay, so we'll do the simplifications of the equations a little later, but the point that we will first make is about the analogy between the various equations. Okay, so for that, what we will do is to try and normalize the equations, that is, to make the equations such that all the dependent variables that we are solving for in these equations, for example, in the x momentum equation we are solving for u, in the y momentum equation we are solving for v, in the energy equation we are solving for T, in the concentration equation we are solving for C. If we can recast these equations in such a way that the variables that we are solving for are normalized between 0 and 1. You cannot normalize both u and v between 0 and 1 at the same time because they have a relative magnitude between each other. So let us say the u is varying between 0 and u infinity. So if I divide u by u infinity, I get a quantity which will vary between 0 and 1, which is what we call as the non-dimensional velocity. Similarly, the temperatures, we have a temperature difference characterizing this as Ts minus T infinity. So suppose if Ts is greater than T infinity, let us say, then Ts minus T infinity is the characteristic temperature difference. So the temperature at any location can be normalized with respect to this Ts minus T infinity. If I take T minus T infinity as the temperature, or the characteristic temperature, so T minus T infinity by Ts minus T infinity, or T minus Ts divided by T infinity minus Ts. So this kind of a normalization will make sure that this whole variable varies only between 0 and 1 inside the boundary layer. So let us write those quantities. Okay, so you have capital U, okay, capital U is u divided by u infinity. So this is a non-dimensional number. This is equal to 0 at the wall and equal to 1 in the free stream. Okay. So let us also define the non-dimensional temperature and concentration in the same way. So if I define a theta, which is a non-dimensional temperature, this is equal to, let us say, T minus Ts divided by T infinity minus Ts. Why are we defining it this way? Because at far field, outside the boundary layer, the T is equal to T infinity. So theta goes to 1 in the free stream. Just like u by u infinity goes to 1 in the free stream, theta also goes to 1 in the free stream. And at the wall, T is equal to Ts, so theta will be equal to 0, similar to this one where u is equal to 0 at the wall. Similarly, you also define, let us say, a non-dimensional concentration. Okay. So non-dimensional concentration, let us look at as Ci with a tilde on top, just to distinguish it from the dimensional one. The Ci tilde is equal to, in the same way, Ci, which is concentration of species I, minus Cis divided by Ci infinity minus Cis is the definition of concentration, non-dimensional concentration. Then when I apply these to the boundary layer equations, let us also do the normalization of the length scales. So if Lc is the characteristic length which is, let us say, the total length of the plate itself. Okay, so x goes from 0 to LC. So the value of capital X, if I define as x divided by LC, then this x will vary from 0 to 1. And the y value, capital Y, has to be normalized with the same length, which will be y by LC. But if we look at the orders of magnitude of x and y, this x is of the order of LC in the whole domain, because it varies from 0 to LC, whereas the area of interest y goes only from 0 to delta. So y is of the order of delta of x. Okay, so we are not interested in anything beyond delta of x. So this is a much smaller quantity as compared to LC. Okay, so y is a variable which is much smaller than x. That you can see from the diagrams that we have drawn here. So on this boundary layer, x has a much larger dimension of LC as compared to y, which has a much smaller dimension, and we have said that the boundary layer approximation is that delta of x is much smaller than x, which will basically mean that y at any location is a small value as compared to x, except in the very close region of the leading edge, which we will not be looking at because that's a singularity in any case, where that delta of x itself tends to 0. We can leave out that region, but in the rest of the region we can say the boundary layer approximation is valid. So we have the y that goes as y by LC, which is much less than the capital X. Okay, so this is your thing. So using these boundary layer approximations, if I write the continuity equation, let us say del u by del x plus del v by del y equal to 0, and if we try to write this in terms of the non-dimensionalized quantities, I'll have this u, I can write it as u infinity into capital U. Okay, I can take it here. Similarly, v, I can write it as small v by u infinity. So this small v can be u infinity to capital U. So if I take out u infinity here, this will become capital U, and this will become capital V. And similarly, if I say small x is capital X into LC, and small y is capital Y into LC, so LC can come out. So if I take out u infinity divided by LC from this equation, then I'll get a del u by del capital X plus del v by del capital Y is equal to 0. And since this quantity is non-zero, the governing equation becomes just this one. So this is your equation of conservation of mass, which gives you del capital U by del capital X plus del capital V by del capital Y equal to 0. So that is your equivalent equation to this. And now here x varies from 0 to 1, y varies from 0 to delta by LC, which is a much smaller quantity, u varies from 0 to 1, and v will vary according to the order of magnitude of u, x and y. Now let us go to the next equation, which is the x momentum equation. So you will have u del u by del x plus v del u by del y is minus 1 by rho del p by del x plus nu del squared u by del x squared plus del squared u by del y squared. So now what happens? In the left hand side, we have one u here, one u here. So if both of them I write it as u infinity multiplied by capital U, I'll get a u infinity square out here. And if this x I write it as capital X multiplied by LC, then I'll get a u infinity squared by LC on the left hand side outside, and all of these quantities will then become non-dimensional. So on the left hand side, I'll be able to write all of these in the capital with a u infinity squared divided by LC. Okay. So let us do that and come back to this page. So you will get a u infinity squared divided by LC multiplied by u del u by del x plus v del u del u by del y. this is equal to, let us write down the del p by del x as it is. We'll normalize it a little later. So 1 by rho del p by del, I'll write it as capital X and write an LC here. Okay, so that we can write down the remainder as we go on, plus you have a nu that is here, and in this you have a del squared u by del x squared and del squared u by del y squared. So in the numerator you have a u, and the denominator you have an x square or y square, so it will become u infinity by LC square multiplied by the non-dimensional quantity. So you will get u infinity divided by LC squared multiplied by del squared u by del x squared plus del squared u by del y squared. Now let us rearrange this. I can take this u infinity squared by LC to the other side, so that the left hand side has no other coefficients. So what will happen? This will remain here. What will happen to this term? I'll get a u infinity squared divided by LC squared into rho, okay, and divided by, multiplied by del small p by del x. Okay, so now the what did I do? I wrote it opposite. So this LC would get cancelled and the u infinity square will come here, 1 over rho u infinity square del p by del x. So now the rest of the equation is non-dimensional, so p divided by rho u infinity squared is a non-dimensional quantity. Okay, so if I define a capital P, which is small p divided by rho u infinity squared, you can verify that dimensionally the numerator and denominator will have the same dimensions or units, and therefore if I write capital P is a non-dimensional pressure which is defined as small p divided by rho u infinity square, then I'll get a minus del capital P by del capital X in this term. So I can write this term in the form of a minus capital del P by del capital X. Okay, so that is for this term. What happens here? The u infinity by LC, if I take it this side, one LC would get cancelled because there are two LCs here and there's only one here, and similarly there are two u infinities here and there's a single u infinity here, so one would get cancelled. So if I take it to the other side, I get nu into L nu divided by u infinity into LC. This is basically what you will have. Now you will find that this in itself is a non-dimensional quantity because this nu has the unit of meter square per second, and this has a meter per second, and this has a meter. So u infinity by nu by u infinity LC is a non-dimensional number. Okay, so this we would call it as 1 over RE, where this is RE is the Reynolds number. We'll understand why that is so. If I do that, then this whole thing is non-dimensional. So what is this? RE is nothing but u infinity LC divided by mu, and there will be a rho here because this mu is a mu by rho. So what is this? So we talked about the Reynolds number in the previous class, talking about laminar and turbulent flows. We'll go a little bit in more detail in the present class. So what we will see is that this can be rewritten as rho u infinity squared divided by, so there is multiplication and division by u infinity, so I'll have a mu u infinity divided by LC. Okay, so what have I written there now? This rho u infinity square, suppose I multiply and divide by the flow area or the areas corresponding. Okay, so now what you have is there is a rho u infinity A multiplied by u infinity, so I can write this as rho u infinity A into u infinity. Okay, and here I'll have mu u infinity by LC into A. So what do you have? This is an m dot and this is a u infinity. So m dot u infinity is nothing but the momentum flow rate, okay, which is basically the momentum that is present in the free stream. Okay. So this is an inertial term. Okay. So this is basically a term corresponding to the inertia of the free stream. Let me write it in full. Okay. So this is an inertial force exerted by the free stream on the plate. If A is the area of the surface of the plate, then m dot u infinity into A is nothing but momentum transfer exerted by the free stream onto the plate. So it's in some sense the inertial force exerted on the plate. What is this? This is, if I write this as an approximation of del u by del y in the direction of perpendicular to the plate, then the velocity varies from u0 to u infinity over a length of, let us say, delta. But if I write it in terms of LC, in some sense this multiplied by mu is actually a viscous force. Okay, so this is viscous. So the Reynolds number stands for a ratio of the inertial forces on the plate to the viscous forces on the plate. Okay, so when the Reynolds number is large, then the inertial forces dominate over the viscous forces. Then the disturbances that are introduced to the flow cannot die down that easily, and therefore the flow can become unstable and become turbulent. But when the viscous forces are dominant, the Reynolds number is small, then the flow, whatever disturbances you introduce into the flow are controlled by the viscous forces that are present, and therefore the oscillations die down and the disturbances are controlled, and therefore the flow remains stable. So this Reynolds number is therefore a quantity which determines whether the flow would be inertia dominated or viscous dominated, and therefore would be unstable or stable. Okay, so that is the term that you have. So your viscous term here actually is multiplied by 1 over Re. That is the thing that you get here. So if I put all of this into the equation and rewrite this equation, the equation actually becomes u del u by del x plus v del u by del y is equal to minus del p by del x plus 1 over Re of del squared u by del x squared plus del squared u by del y squared. Okay. If I do the same thing to the y direction, I'll again get u del v by del x plus v del v by del y is equal to minus del p by del y plus 1 over Re times del squared v by del x squared plus del squared v by del y squared. This is what you get, and you already have the continuity equation, or the conservation equation, or conservation of mass equation, which says del u by del x plus del v by del y equal to 0. Now these are the three equations, conservation of mass and conservation of momentum in the two directions, x and y directions, in the non-dimensional form. Okay. So now if I try to do similar non-dimensionalization also to the energy equation and the species equation, I'll get u del t by del x plus v del t by del y is equal to alpha del squared t by del x squared plus del squared t by del y squared plus, let's say, q dot triple prime generation. Now in the case of a boundary layer flow, this term is absent, so I can actually leave out, because there is no heat generation defined in the problem. It's only a flow past a flat plate, a free stream. There is no heat generation in the fluid, therefore it can be written like this. Now if I write theta as t minus ts divided by t infinity minus ts, where ts and t infinity are both constants, then this whole equation, instead of t, I can write t minus ts by t infinity minus ts. Then the t infinity minus ts will be there in every term, and therefore would get cancelled, and therefore this whole equation can easily be written with theta replacing t without any changes. And in addition to that, if I write the non-dimensionalization of u, v, x and y, then I'll get u infinity divided by LC multiplied by capital U del theta by del x plus capital V del theta by del y is equal to alpha, and there is a divided by LC squared that will come from this equation, multiplied by del squared theta by del x squared plus del squared theta divided by del y squared. Now this u infinity by LC, you bring it to this side, then what happens is it becomes alpha multiplied by or divided by u infinity LC. Okay, so if I write this as nu by u infinity LC multiplied by alpha by nu. Okay, so this is the thing that you get. Now this is nothing but your 1 over RE that we just wrote, and this term alpha by nu is actually 1 over Prandtl number, where Prandtl number is defined as, the Prandtl number itself is defined as nu by alpha. Okay, so this 1 by Prandtl number is nothing but alpha by nu. Okay, so this will be 1 over RE and 1 over PR. So what do you get? You get this entire equation replaced with the non-dimensional form, which will basically say, I can remove these and simply write 1 over REPR in this equation. Okay, so that is your energy equation in the non-dimensional form. If you compare it with these equations, you get a very similar left hand side, except that here there is u, here there is v, and here there is a theta. Otherwise the left hand side is very similar. And on the right hand side you have del squared, here there is a u, here there is a v, and here there is a theta. So that looks very similar. The coefficient that multiplies it in the case of this equation is 1 over RE, momentum equation, it is 1 over RE, and in the case of the energy equation it is 1 over REPR. The difference you can see is that it is alpha by u infinity LC instead of nu by u infinity LC. Though there is a ratio of alpha by nu, or 1 over Prandtl number. This Prandtl number is basically the one that distinguishes or that characterizes the relative diffusivities of momentum and energy, because this nu, kinematic viscosity, in some sense is the diffusivity of momentum, as we saw in the basic definition of Newton's law of viscosity. That is this equation. The tau is equal to minus mu del u by del y. So the mu, or in other sense mu by rho, is in or kinematic viscosity is mu by rho, which has the units of meter square per second, similar to alpha. So this mu it has to do with the diffusivity of momentum. So the mu by rho is actually appropriate in the appropriate units, the diffusivity of momentum. In the same way, k by rho Cp, which also has the same units, meter square per second, which is alpha, is the diffusivity of energy. And in the same way, here d, which has the units of meter square per second, is the diffusivity of mass. So these three are terms which are cousins of each other in the various transport mechanisms. So in transport of momentum it is nu, in transport of energy it is alpha, and in the transport of species it will be d. So in this particular case, the ratio nu by alpha is the ratio of momentum diffusivity to thermal diffusivity. So if this ratio is 1, then you can say that the momentum and energy diffuse at the same rates, and therefore the diffusivities are identical. So if the mechanisms of thermal diffusion and momentum diffusion are similar in a particular substance, then the order of magnitude of nu and alpha would also be similar, and then Prandtl number would be of the order of 1. Otherwise, the Prandtl number would be deviating from 1, and then this right hand side would have a different effect on the equation as compared to when Prandtl number is 1. So that is the thing. So the Prandtl number is the one that distinguishes the momentum diffusion from thermal diffusion, and when Prandtl number is 1, we can say that this equation is more or less the same as this equation, particularly when the pressure gradients can be neglected or pressure gradients are 0 in certain situations. If the pressure term, if this can go to 0 in any particular flow situation, which actually happens in the case of a parallel plate flow or of a flat plate boundary layer flow, then the equations for momentum and energy have the same form, except that instead of u and v that are there in the momentum equation, there is theta in the energy equation, and instead of Re there is an RePr, and if Prandtl number is 1, then these equations are identical. Their boundary conditions are also identical. That is the way we have defined them. That is, capital U and capital V are zeros at the wall, and U is 1 at the far field, and theta is 1 at 0 at the wall and 1 in the far field. In the same way, if I write it for concentrations, U del C I by del X plus V del C I by del Y is equal to D times del squared Ci by del X squared plus del squared Ci by del Y squared. And if I don't write any source term, that is, there is no chemical reaction that's happening in the free stream, then this is the equation. So if I write Ci tilde is Ci minus Cis divided by Ci infinity minus Cis. Now Cis and Ci infinity being constants, I can simply replace the Ci by Ci tilde in all the terms. The extra term that comes Ci infinity minus Cis will get cancelled in the terms. Then the equation will look very similar to the energy equation when I write the U and V and X and Y in the non-dimensional form. So basically what I'll get is capital U del Ci tilde by del X plus capital V del Ci tilde by capital Y del capital Y is equal to D by U infinity LC multiplied by del squared Ci tilde by del X squared plus del squared Ci tilde divided by del capital Y squared del Y squared. Now you can see, now this term is nothing but nu by U infinity LC multiplied by D by nu, and this term is 1 over nu by D, and this nu by D is called the Schmidt number. Okay, so now nu as well as D have the same units, meter square per second, and therefore this is a non-dimensional number, which is the ratio of momentum diffusivity to mass diffusivity. Just like you had momentum diffusivity to thermal diffusivity, you have momentum diffusivity to mass diffusivity ratio here. So this is Schmidt number. So this becomes 1 over Re, and this becomes 1 over Sc. So you have a 1 over ReSc that will come in this place. So I can remove this and write 1 over ReSc. So you see that the governing equations for transport of momentum, energy and any species have the same form, and if Schmidt number is 1 and there are no pressure gradients in the momentum equation, then all of these equations are exactly similar to each other, and with the same boundary conditions, and therefore their solutions would also be the same values. So that is what one understands by Reynolds analogy. So Osborne Reynolds looked at these equations and basically came up with what is called the Reynolds analogy. So this happens when Prandtl number equal to 1 and Schmidt number is equal to 1. So the 1 over REPR and 1 over RESC become identically equal to 1 over RE in the momentum equation and the species equation. Then the mechanisms of transport of momentum, mass and energy are identical, and their magnitudes in the non-dimensional form are also identical, because their boundary values are 0 at the wall and 1 in the free stream for all these quantities, and therefore they have exactly the same solutions. And therefore the solution that you get for wall shear, the shear stress at the wall, can be used for the heat flux at the wall as well as from mass flux at the wall. So this is what we understand by Reynolds analogy. So by Reynolds analogy we mean that the mechanisms of momentum, heat and mass transfer as well as their magnitudes are identical, and therefore the result of fluid flow can be applied numerically. Exactly the same values can be applied to the heat transfer as well as mass transfer. Okay, so that is the Reynolds analogy. We'll come to the Reynolds analogy a little bit more in detail as to what we understand by the non-dimensional numbers that correspond to momentum transfer, heat transfer and mass transfer. The momentum transfer is quantified by tau, and if I normalize it with respect to rho u infinity squared by 2, okay, because the tau has the same units as pressure, which is the force per unit area, and so it's dimensionally consistent with rho u infinity square. So if I divide it by the kinetic energy of the free stream, then I get a quantity called Cf, which is called the skin friction coefficient. Okay, so the non-dimensional momentum flux, the momentum flux is tau, and the non-dimensional momentum flux is tau divided by half rho infinity square, is quantified by a quantity called the skin friction coefficient. Okay, so now this tau is actually mu times with a negative sign del u by del y at any location in the boundary layer. So this shear stress at any location is quantified by the skin friction coefficient at that location. Okay, so if I have a boundary layer which is like this, at different locations, that is different values of x, you will have different values of del u by del y and therefore different values of Cf. So there is a Cf variation with x. So Cf is a function of x, but the Cf at any location will be given by this, and this is the skin friction coefficient. So at any location it's called the local skin friction coefficient. Okay. We can also get an averaged skin friction coefficient by integrating this tau over the entire area of the plate, okay, and dividing it by half rho u infinity squared. Then you would get a Cf bar, which is an averaged skin friction over the entire plate. Okay, so this is the average skin friction coefficient. Okay, so you have the non-dimensional shear stress given in the form of local or averaged skin friction coefficient. In the same fashion, the heat transfer is given by minus k del T by del Y, which is also equal to H into Ts minus T infinity. Okay, and so the normalized form of this would be if I write minus del T by del Y with the Ts minus T infinity on this side, because we are writing actually for theta, it will become minus del theta by del Y. Okay, so this T minus T infinity Ts divided by T infinity minus Ts would actually give me the T minus Ts divided by T infinity minus Ts would actually give me del theta by del Y, this del y, so there needs to be an LC here which would go up there. This would actually become HLC by KF. Okay, so now this is a number which we have already seen as the Nusselt number, that is the number of times by which the heat transfer coefficient increases in the presence of convection over the case with pure conduction. So this Nusselt number is actually a representative of the non-dimensional heat transfer or non-dimensional heat flux at the surface. Just like skin friction coefficient is the representative of the non-dimensional momentum flux at the surface, the Nusselt number is representative of the non-dimensional heat flux at the surface. Okay, and similarly, the non-dimensional mass flux can be defined in terms of mass transfer coefficient Hm into Lc divided by D, where mass transfer coefficient is the quantity which is defined like minus d del C rho d rather del Ci by del y is actually equal to Hm into Cs minus C infinity. So in this, if I can redefine these quantities and bring them together, then I'll get Hm into Lc by d, which is normally called the Sherwood number. Okay, so under the conditions of Reynolds analogy, where the Prandtl number and Schmidt number are equal to 1, the non-dimensional gradients for all these three variables, because the variables are identical, the boundary values of these variables are identical, and therefore the solution for all of these variables will be identical, and hence their gradient at the boundary del by del y of the concentration or the temperature or the velocity, the non-dimensional velocity, non-dimensional temperature, non-dimensional concentration would all be the same at the boundary. Therefore, your Cf or rather Cf by 2, this half going up here because there is no half in these cases, Cf by 2 would actually be equal to the Nusselt number, would actually be equal to the Sherwood number. So the Reynolds analogy basically says when Prandtl number is equal to 1 and Schmidt number is equal to 1, then the non-dimensional velocity gradient at the surface represented by Cf by 2 would be equal to Nu and would be equal to Sh. And for Nusselt number and Sherwood number also, we should be able to define a local value because the H varies with x and Hm varies with x, and we can also define an average value by integrating the total heat transfer or the total mass transfer over the entire plate. So you get Cf bar, Nu bar and Sh bar, just like you have Cf, Nu and Sh, and then we can give a relationship between the averaged quantities also in the same fashion using the Reynolds analogy. So when the Prandtl number and Schmidt number are equal to 1, then we say the Reynolds analogy is valid, then all of these quantities can be equated to each other. So this is one similarity or analogy that we normally make use of in understanding these three sciences: fluid mechanics, convection heat transfer and convection mass transfer, and similarly conduction heat transfer, conduction mass transfer and viscosity. These terms are these equations and therefore their solutions are very similar to each other, and therefore the analogy between them can be used, particularly when the Prandtl number and Schmidt number are equal to unity. Okay, and that happens in the case of gases, where all of the mechanisms of momentum transfer, heat transfer and mass transfer are because of random motion of the molecules, and therefore their orders of magnitude are all similar. Okay, but for other substances this would not be the case, and we need to handle it differently for those cases. So in place of Re we would use an RePr, in place of Re we would use an ReSC for mass transfer, and we will be calculating the various things. So now from this we will try to get the orders of magnitude of the boundary layer thickness and hence the Cf and Nu and Sh for the cases of a boundary layer when the Prandtl number is equal to 1 first, and then we'll look at heat transfer from the wall when Prandtl number is not equal to 1. So what will be the changes that will happen in the mechanisms of heat transfer because of the changes in the boundary layer thicknesses, the diffusivities being different at the boundaries in the fluids. because the momentum diffusivity would not be the same as mass diffusivity or thermal diffusivity. What are the changes that will come to the boundary layer behavior? These things we'll be looking at as part of the next class. So in today's class, we'll stop at this point with the understanding that the governing equations show analogies between each other, and when certain parameters such as the Prandtl number or Schmidt number are unity, then the solutions collapse onto each other when they are particularly in the non-dimensional form, so that you can use one solution to represent. So you need to solve only one of the three equations, and the same solution can be used for the other equations as well using the Reynolds analogy. So we'll stop at this point and continue our understanding in the next class. So before I close, let me greet you showing my face. Thank you very much. We'll meet again in the next class. Now the Dean has put up the new schedule for the semester, that by 24th we should be completing all the online uploading of materials, which basically leaves me with about 7 lectures in 7 days, and therefore I would be putting up 1 lecture each day over the next 1 week. But that is a constraint on my side. But from your side, your semester is going to begin on 2nd of July, and when you come back here, you need to come prepared with all of these lectures, so that we'll have the problem solving and evaluations only when you come back here. So when you come back to IIT, we'll only have tutorial classes and discussion classes, and we will have minor test and major test and the quiz 3. No other activity will take place. I will not be giving you any more lectures when you come here. So please use these lectures with the time that you have available, so that when you come back, you come prepared for completing the semester in a short duration. Okay. So we'll close at this point, meet again hopefully with another lecture tomorrow morning. Thank you. Bye-bye.